And these complexes, we need to match them in terms of their magnetic property or as well as in terms of the type of complex formed, whether it is inner orbital complex or outer orbital complex. Let's see one by one. This is a very important objective. You need to listen to this carefully. Here the central metal is nickel and that is there in +2 oxidation state. Then what is the electronic configuration of nickel in +2 state? It is nothing but 3d8 4s0. Then here the 8 electrons in 3d we can write like this, isn't it? But here the ligands are cyanide, which is a strong ligand. So in presence of strong ligand, these electrons get paired up against the Hund's rule. So we get the electronic arrangement like this, in which there are no unpaired electrons. So this is 3d and there is vacant 4s, there is vacant 4p also. So as this is to be coordinated with 4 ligands, definitely 4 orbitals from here, they undergo hybridization in order to form 4 dsp2 hybrid orbitals. So what is the hybridization of the nickel in this particular complex? It is dsp2 hybridization. So as the inner d orbitals are involved, this is inner orbital complex. As there are no unpaired electrons, this is diamagnetic in nature. So what is happening here? Always in presence of strong ligands, the reshuffling of electrons takes place or the pairing of electrons takes place against the Hund's rule. And then only some required number of orbitals they undergo hybridization to form hybrid orbitals and later on the complex is formed. And the next one, it is again the nickel complex where nickel is in +2 state. So its electronic configuration becomes 3d8 4s0 and the 3d8 configuration we represent like this. And as we know that even ammonia is an example of strong ligand. So what happens? Definitely the electrons get paired up. So this is 3d, there is vacant 4s, 4p as well as 4d. But in this particular case, as nickel is to coordinate with 6 ammonia ligands, so definitely 6 orbitals of nickel are involved in bonding. So here it is 1 s orbital, 3 p orbitals and 2 d orbitals undergo hybridization in order to form 6 sp3d2 hybrid orbitals. But remember here, even the ammonia is a strong ligand, there is no requirement of pairing up of these electrons because 1 d orbital of the inner level and 1 d orbital of the outer level cannot be involved in hybridization. It can be either 4s, 4p and 4d or it can be 3d, 4s and 4p because there will be more difference in energy between the 3d orbital as well as 4d orbital. So that is the reason why here there is no pairing of electrons even though ammonia is a strong ligand. So that is the reason this is paramagnetic in nature. As the d orbitals of the outer energy level are involved, this is an example of outer orbital complex. This is a complex of cobalt. Here cobalt is in +3 state and its electronic configuration is 3d6 4s0. The 6 electrons in d orbitals, they are present like this. But here as ammonia is a strong ligand, this pairing of electrons takes place against this Hund's rule. So now in presence of the strong ligands, the electronic configuration becomes like this. So now it is having 2 d orbitals here. Then there is a vacant 4s orbital immediate next to this and 3 vacant p orbitals, isn't it? So then these 2 d orbitals, this 1 s orbital, these 3 p orbitals mixed together in order to form 6 d2 sp3 hybrid orbitals. So here there are no unpaired electrons, so this is diamagnetic in nature. As the inner d orbitals are involved in hybridization, so definitely this is inner orbital complex. So based on the number of vacant orbitals required for the coordination with the ligands and also based on the type of ligands to which it is attached, accordingly the pairing of electrons takes place. And the last one, it is an iron complex where iron is in +3 state. So here the configuration of iron becomes 3d6 4s0. And if it is 3d6 4s0, it is similar to that of the previous one where 6 electrons are there in 3d. And as cyanide is an example of strong ligand, the pairing of electrons takes place against the Hund's rule. So pairing of electrons takes place and there are no unpaired electrons in Fe3 plus in presence of this cyanide ligands. And this 4s as well as 4p orbitals are also involved in the bonding. So here D2sp3 hybridization is taking place, and as there are no unpaired electrons, this is also diamagnetic in nature, and as 3d orbitals are involved in bonding, it is inner orbital complex. So what's our answer here? For complex A, P and R is the correct match. For B, it is Q and S. For C, it is P and R. For D, it is again P and R.